Hello friends, welcome to the basics of digital signal processing. In this session, we'll go through discrete time signals and some elementary discrete time signals. Let us start with the discrete time signals. A discrete time signal is a function of an independent variable, usually an integer, that can be represented as this representation, right? So now here we have to observe that the x-axis is varying with respect to the n, where n is a discrete variable. That means -3, -2, -1, 0, 1, 2, 3. These are the discrete values we are having. Only at these locations we are going to have definition for the amplitude. So y-axis is the amplitude. At -3, so amplitude is 1.4. At 0, the amplitude is 2. So like that for all other values we are going to have over here. Now there are some other ways of representing this discrete signal. So first one under that is functional representation. So it is given by x of n is equal to 1 for n is equal to 1 comma 3, 4 for n is equal to 2, 0 elsewhere. Right? So that means this is a functional format of representing a signal. The same signal can also represent in the another form. That's the second one, the tabular representation. Tabular representation. So in that n is what the value we are having. So starting from -2, -1, 0, 1, 2, 3, dash, 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 both on the positive side as well as on the negative side, dash, 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 we are having. Now if we represent the same thing in the tabular form, we are going to get at location 1 comma 3, at location n is equal to 1 comma 3, its value is equal to 1. So location 1 and location 3, the values are equal to 1. And at n is equal to 2, at location 2, the value is equal to 4. So at location 2, the value is equal to 4. And elsewhere it is equal to 0. So that's why 0, 0, 0. And if we proceed further also 0, 0, 0. Right? So this is called the tabular way of representing the same function. Now getting into another one. So sequential representation. Now in this case, a finite sequence is being given by x of n is equal to 0, 0, 1, 4, 1, dash, 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 dash. Here we are going to have, and here we are going to represent the arrow mark which indicates the origin. So origin in the sense at n is equal to 0, what is the value? That's what we call the origin. At n is equal to 0 location, we call that as the origin. At location 0, it's having the value 0. At location 1, it's having 1. At location 2, the value is 4. At location 3, value is 1, and so on we are having. Right? So now finite sequence is also given by x of n is equal to 0, 1, 4, 1, dash, dash, dash. So this is the origin. That means from 0, location 0 and onwards, we are having the value representation. Right? This is also sequential representation. And x of n, another way of representation, 3, 2, 0, 1, 3, 5, 7 values. And here 1 is the value where the n is equal to 0 is there. That means at n is equal to 0, the value is equal to 1 we are having. So this is also a sequential representation. Now getting into some of the elementary discrete time signals. So first listing of all of them: unit sample sequence, then unit step sequence, unit ramp sequence, and exponential sequence. Let us go through one after the another. First starting with the unit sample sequence. So it is denoted by delta of n, and it is given by delta of n is equal to 1 for n is equal to 0, 0 for n not equal to 0. So with respect to graphical representation, this is what the representation we are having. Only at the origin its amplitude is equal to compulsorily 1, and in all other locations its value is equal to 0, and that is what is being shown over here. So at origin location 0, the amplitude is equal to 1, and in all other locations, both on positive and negative side, the values are equal to 0. Now unit step sequence denoted by u of n, and it is given by u of n is equal to 1 for n greater than or equal to 0, 0 for n less than 0. That means from 0 and onwards, positive side, the amplitude is 1, and towards negative values starting from -1 up to any value negative values, its value is equal to 0. That is what is shown over here. From 0, 1, 2, 3 positive side, the amplitude is 1, and -1, -2 towards negative side, the value is equal to 0. This is called the unit step sequence. Now getting into the unit ramp sequence, so it is denoted by UR of n, and it is defined as UR of n is equal to n for n greater than or equal to 0, 0 for n less than 0. So that means again from 0 and onwards towards positive values of n, we are going to have value for the ramp sequence. For negative valued locations of n, we don't have any values, that will be always equal to 0. The same thing is observed over here. At n is equal to 0, the value is equal to 0. That is, the value is same as n. At location 1, that is n is equal to 1, amplitude is equal to 1. At n is equal to 2, amplitude is equal to 2. At n is equal to 3, amplitude is equal to 3. If 4 and onwards, if we can continue, if n is equal to 4, obviously amplitude will be equal to 4 we are going to have. So that is what the ramp is going to say. So n for n greater than or equal to 0. Whatever the location value we are having, the same will be the amplitude of the signal. Now getting into exponential signal. So it is given by x of n is equal to a to the power of n. If parameter a is real, then x of n is real signal. Right? For example, we have taken e to the power, exponential e to the power we have taken. So if the power is positive or the negative, what we are going to get? So these are the realizations for that one, right? So the another way of representation is if the parameter a is complex valued, then its expression is given by a is equal to r e to the power of j theta. So that implies x of n is equal to r e to the power of j theta whole to the power of n. Right? A will be this value, a to the power of n, in the sense to the whole to the power of n, that becomes r to the power of n e to the power of j theta n. Right? Again, retaining r to the power of n, expanding this exponential value to the sine and cosine format, we are going to get r to the power of n into cos theta n plus j sine theta n. Right? Within this one, the real part of the representation is r to the power of n into cos theta n. Complex valued representation is, that is, we call it as the imaginary part. So r to the power of n into j sine theta n. So that is what is being represented over here. XR represents the real valued representation. Then XI indicates the imaginary valued representation. Thanks for watching.